Hey there, have you ever felt completely overwhelmed by a problem? Like you're standing in front of a giant wall of combination locks and you know one of them opens a door to something amazing, methodical, reliable, but kind of slow when the problem gets really, really big. We call them classical computers and they've changed our world. But what if I told you there's another way? A way to cheat, almost a way to find the right combination without trying them all. If you input that secret number, it flashes true. Any other number, it says false. But you have to try every single combination one by one. That's pretty much how our computers work today. This isn't science fiction, it's quantum computing, and I know what you might be thinking. So for 1,000,000 items, maybe 20 tries. You've probably seen the headlines, quantum computers will try every possibility at once. The next biggest group picks B, an exponential speedup, and today I want to take you on a journey to uncover the real story. It is a story that is less about magic and more about a strange and wonderful kind of geometry. A story about how to find a needle, not in a haystack but in a universe full of them, and it all starts with a little quiz, an infinite parallel universe in a microchip. It sounds magical, like it can solve any problem instantly. Well, I used to think that too. It's a neat summary, but it's also a bit of a lie, a beautiful, tempting lie. Imagine I have a secret function, a black box. It's programmed to recognize one specific number out of, say, 1,000,000. Now, using your laptop, a classical computer, how would you find that secret number? You'd have no choice but to guess, right? You try 1, false. You try 2, false. You keep going, on average. You'd have to try about 500,000 times before you hit the jackpot. In computer science terms, if the list has n items, it takes about n2 tries. The bigger the list, the longer it takes, in a straight, predictable line. Okay, here's the quiz. What if you had a quantum computer? How many tries would it take then? Would it be just one try because it checks them all at once? Be a lot fewer, maybe something like the logarithm of n? C, or something else entirely? Every time I've asked this, most people, full of that pop science optimism, go for a one try. Both are wrong, and this is the first big secret of quantum computing. The answer is the square root of n. For a list of 1,000,000 items, a quantum computer wouldn't take one try or 20 tries. It would take about 1,000 tries, a huge improvement over 500,000 for sure. But it's not instantaneous, it's not magic, it's a specific quantifiable advantage. This is called a quadratic speedup, and it's the real promise for a huge class of problems. This specific trick is called Grover's algorithm, and understanding how it works peels back the curtain on what quantum computing really is. It's not about doing the same old thing in parallel, it's about playing a completely different game. To understand that game, we need to forget everything we know about bits. It can be up or it can be down, simple. Our entire digital world is built on bits, ones and zeros, on or off. Yes or no, a bit is like a light switch. If you have, say, 3 qubits, you can represent all 8 possible combinations 0, 0, 0, 0, 0, 1, etc. in a single quantum state. With 20 qubits, you can represent 1,000,000 states, and which one it snaps to is a matter of probability. The goal of a quantum algorithm is to choreograph a delicate dance of these arrows, so that when we finally decide to look, they are all but guaranteed to snap into the position that holds the answer we want. If the arrow was pointing mostly up, it'll probably snap to 1, the numbers describing the direction of these arrows. They can be negative. If it was at that perfect 45-degree angle, it's a 50/50th shot. When you measure, the probability depends on the square of these numbers, and 1 squared is 1, minus 1 squared is also 1. So from the outside, a positive arrow and a negative arrow look identical. They give you the same probability of collapsing to 0. With 300 qubits, you can represent more states than there are atoms in the known universe. It allows for something incredible: cancellation, interference. Just like how two sound waves can cancel each other out, two quantum states can be made to cancel each other out. Imagine a circle. An arrow pointing straight right could represent O. It can be a little bit of O and a lot of 1. Now let's use it to find our needle in the haystack, or a perfect 45-degree angle, an equal mix of both. This in-between state is called superposition. An arrow pointing straight up could represent 1. Those are our classical states, our definite answers. A quantum bit or qubit is different. Think of it less like a light switch and more like a dimmer knob. It's not just on or off. It can be somewhere in between. But even that analogy doesn't quite capture it. The best way I've found to think about it is with an arrow, a vector. A qubit can be an arrow pointing in any direction within that circle. This is where that all possibilities at once idea comes from. Sounds powerful, right? But here's the catch, and it's a big one. You can never see this superposition. The moment you try to look at it to measure it, the whole thing collapses. The arrow instantly snaps to one of the definite positions, either straight right O or straight up 1. So a quantum computer is a machine that carefully manipulates these arrows, these state vectors, in a vast high-dimensional space we can't see. The whole game is about controlling probabilities. And there's one more bizarre rule to this game. Think about that. An arrow pointing right is 1, 0. An arrow pointing left is -1, 0. But inside the quantum world, they are fundamentally different states. And this difference, this ability to use negative numbers, this phase is the secret weapon. This is the toolbox, not parallel processing, but superposition, measurement, and interference. Okay, back to our million combination locks. One of them is the right one. How does Grover's algorithm find it? Step 1. Create the fog. First, we set up our quantum computer. If we have 1,000,000 possibilities, we need 20 qubits. We put them all into a perfect balanced superposition. This creates a state vector where every single one of the 1,000,000 possible answers has the exact same tiny probability. It multiplies it by -1. The landscape still looks perfectly flat, but we've secretly marked our target. We've put a tiny invisible kick me sign on the back of the right answer. Imagine a vast flat landscape of possibilities. Our state vector is a fog spread evenly across the entire landscape. There are no clues yet. Every state is at the same positive height except our target, which is now at a negative height. The average height is just slightly below the height of all the wrong answers. The fog is starting to thin in some areas and thicken over our target. The probability of finding the correct answer is now a little bit higher. We run the oracle, which flips the sign of our now amplified target back to negative, and then we do the big flip again, amplifying it even more. Step 2, the magic oracle. The state vector, our arrow, takes a small, precise step towards the direction of the correct answer. Next, we need a way to mark the correct answer. This is our oracle. The fog has cleared and has become a single towering peak. The probability mass gets sucked out of all the wrong answers and funneled, step by step, into the one right answer. Remember our mystery function that returns true for the secret number? We build a quantum version of that. Not by checking every piece of hay, but by making the needle sing a different tune and then amplifying that tune until it is the only thing we can hear. For most things, like sending emails or watching cat videos, they're perfect. Quantum computers are special tools for special problems. Problems in drug discovery, materials science, financial modeling, and yes, breaking certain types of encryption. It's a shortcut through reality's underlying geometry, but this quantum oracle doesn't shout, "Here's the answer." That would be too easy, and it would collapse the whole system. The wrong answers, which were slightly above the average, get flipped to be slightly below it, but our target answer, which was way below the average, gets flipped way up high above it. It feels like we've spent our whole history walking on a 2D map, only to discover that reality has a third dimension we never knew we could access. These diagonal paths, these quantum shortcuts, have been there all along. Instead, it does something much more subtle. When it finds the component of our state vector that corresponds to the correct answer, it just flips its sign, and we're just now learning how to navigate it. We're building the ships, drawing the maps. We don't know all the places we'll go, but the journey has just begun. From the outside, nothing has changed. The probability of finding the answer is still the same, remember. X squared is the same as x squared. It's a bit like taking the entire landscape and flipping it upside down, using the average height of the landscape as the mirror. Step 3, the big flip. This is the genius part. We now perform a second operation. Think about it. So what happens when we flip everything around this average? In one move, we've taken the amplitude of our target and amplified it while slightly reducing the amplitude of everything else. Step 4, repeat, and now we just do it again. Each cycle is like a step, a rotation in this high-dimensional space. We repeat this dance, flip the target, flip the average over and over. After about 1,000 steps for our million item list, 4 times the square root of n to be precise, our state vector will be pointing almost directly at the correct answer. Now we measure, and with near certainty, the system collapses to the one state we've been looking for. We've found our needle. So what does this all mean? It doesn't mean our laptops are obsolete. For me, learning this changed how I see the world. The world isn't just a series of definite yes or no's. It's a swirling sea of potential and probability.